Hello guys, and welcome to the Smart Video Lab. I'm here with the Unit 5 test review. I'm going to be showing you guys how to do the problems on there. This video is only going to cover the first three problems. Hopefully I'll be able to make others later, but for right now that will have to do. So let me get my pen ready. So whenever I start a test review, I put the name as key. When you guys are math teachers someday, you can do that because you'll be so confident that you can say it's the key and everything's going to be right. But you guys are pretty smart, so maybe you could do that now, but I prefer that you put your name so that I know who did it. So number one says a simple one-celled organism divides into two identical cells every 30 minutes. So we got this little organism, simple one-celled, and every 30 minutes it splits into two. And then those two, after another 30 minutes, each split into two more. And that guy also does the same, and so on. And we could draw a tree diagram representing each simple-celled organism and how it divides into two more every 30 minutes. Now, part A asks if 6 of these organisms are present in a sample now, how many will be present after 60 minutes? So in my picture, with one organism, this was at time 0, this was after 30 minutes, and this was after 60 minutes. So one organism after 60 minutes split into 4. So if I start with 6 and they each split into 4, that's going to be 24 organisms that will be present after 60 minutes. And you could have also thought of that this way. Okay, I start with 6, then I get twice as much as that after 30 minutes, so that's 12. Twice as much of that after 60 minutes, that's 24. Or you could have said, okay, I start with 6, they're doubling, and 60 minutes is 2 30-minute time periods, so 6 times 2 squared is 6 times 4, which is 24. Different methods of showing the same solution there. So our now next rule tomorrow the situation is next equals now times 2 starting at 6. And since we're multiplying in the now next rule, we know this is exponential growth. So cool thing about exponential growth is standard form of an exponential function, the explicit form, is always y equals a times b to the power of x. We just have to figure out what a is, the starting value in any given problem, and what the specific value for b is, and that's the common ratio. Or you could think of that as the growth factor if it's growing, or the decay factor if it's decaying. But in a now next rule, it's next equals now times b starting at a. So everything that we've done this unit is summarized by these two rules, the recursive formula and the explicit formula. We already wrote the recursive now times 2 starting at 6, so I know that that 2 is my b for this specific problem, my growth factor, and 6 is my a, my starting value. So my y equals rule is going to be y equals 6 times 2 to the x. And that represents this situation where y represents the number of organisms after x, which represents the number of 30-minute time periods. And that makes sense because y depends on x. That's typically how we do it, periods. Typically how we do it is y depends on x. So obviously the number of organisms, y, depends on the time periods, x. How many organisms will be present in the sample after 2 hours? Well, let's just use our rule. Y equals 6 times 2 to the x. So that's going to be, in this specific case, y equals 6 times 2 to the 7th, right? No, that's not right, because 7 hours, but x represents the number of 30-minute time periods. So 7 hours is how many 30-minute time periods? Well, that's 14 30-minute time periods, because each hour is 2 30-minute time periods. So we actually have to do 6 times 2 to the 14th power. which is 98,304. And I'm getting ahead of myself because I skipped part D, which says use the rules from part B and C to complete the table. So obviously we start with 6, then 12, then 24. I'm just multiplying by 2 every time. Then 48, and then 96, and 192. Sorry about that, guys. How part F says, use the table above to graph the function on the grid. Be sure to label the axes and title your graph. So I'm going to focus on that first. Let's label the axes and title our graph. So x-axis, this is going to be number of 30-minute time periods. I can't spell periods today for whatever reason. Periods. Doesn't work. And let me get this out of the way. The y-axis is going to be number of organisms. So I'm going to change colors to orange because orange and blue are complementary colors, and that will make this graph pretty. Actually, let me finish the scale in blue, and then I'll use orange to plot the points. So what's a good scale for my x-axis? The number of 30-minute time periods. It probably makes sense to go by 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'll stop there. That's good enough. Now, to know the scale for my axis of organisms, I need to know how high I'm going to be going. In other words, I need to know how many bacteria there's going to be after 10 30-minute time periods. So that would be 6 times 2 to the 10th, which is, let me pause the video while I calculate. 2 to the 10th is 1,024 times 6 is 6,144 bacteria that are going to be present. So I need to go all the way up to 6,000 on the y-axis. So I'm going to choose to go by a scale of 500. So remember, you have to stay consistent once you pick your scale. I can't go one block is 500 and the next block is 200. That's just not mathematically correct. Number lines are always divided up in equal portions. So if I start with 500, I've got to go to 1,000, and 1,500, 2,000, 2,500, 3,000, 3,500, 4,000, 4,500, 5,000, 5,500. Ooh, that was a little off. Up to 6,000. So now I can get out my orange marker that I was so eager to get out earlier because I like to make things pretty. Yeah, I'm still a man. Don't judge me. So after 0 30-minute time periods, there was 6 organisms present. So that's really hard to plot on this graph, but I'm going to put it there. It's about the best I can do. After 1 30-minute time period, there was 12, and this is all coming from the table. After 2 30-minute time periods, there was 24. After 3, there was 48. So after 4, there was 96. After 5, 192. And these may be a little off, but I'm just doing the best that I can. So after 6, that's going to be 192 times 2, which is 384. So after 6, there's 384. So we're getting a little closer to 500. Then after 7, that's going to be 384 times 2, which is 768. So at 7, there's 768. So now we're above 500, right in there somewhere. Now after 8, multiply that by 2, we get 1,536. So now we're above 1,500 by just a little bit. After 9, we're up to 3,072. So I go all the way up to just above 3,000. And then after 10, we're up at 6,144 as we figured out earlier. So above 6,000 up there. So you can see it grows kind of slowly at first, but then very rapidly once we get up above like 6 30-minute time periods. And that's a horrible curve, but you get the point. You guys can draw better ones. So that's exponential growth right there. It starts off slow and then it gets faster and faster and faster as we get to higher values because we're multiplying. So now number 2 and 3 are a little bit hard. We never really did any like this in class, but you guys are smart. You can figure it out. I'm going to show you a little trick. The key is to first figure out what's the starting value. Where does this graph start? And we're asked to write an equation for each graph. So if I look at this graph, it starts at a point 0, 1/4. And I know it's 1/4 because it's just below 1/2, so I'm going to say, all right, it's like halfway between 0 and 1/2, so 1/4. I need to find another point. Well, actually, let's start with this point. This point tells me that when x is 0, y has to be 1/4. In other words, the starting value is 1/4. And let's go back up to our other example. In this example that we were looking at here, this rule, when x is 0, 2 to the 0 is 1. 1 times 6 is 6. So we know 6 is the starting value because that at x is 0, we get 6 out. So for my rule here, I know that it's going to be y equals 1/4, that starting value, times some common ratio to the power of x. Now I have to figure out what that common ratio is. So I need to find another point on this graph, another nice point. And there's one right there. That's pretty nice to tell. I can definitely tell where that is. And that is at 2, 9. So now I'm going to use that point to help me. This 2, 9, this is an x value and this is a y value. So what that tells me is if I use this rule here that we're trying to figure out, it's going to be 9 equals 1/4 times something we don't know. I'm going to leave it as a parentheses to the power of 2. So we have to figure out what value could go into this parentheses to make this equation true. So 9 equals 1/4 times something squared. So first of all, I have to think what number fits in the parentheses that if I multiply by 1/4, I get 9. And the only number that can multiply by 1/4 to give me 9, or divide by 4 to give me 9, is 36. So I know that once I'm done with this part here, I need to get 36. So now we have to think what number squared is 36. And so we can see that 6 is the number that has to go in here. And let's test that now. 6 squared is 36 times 1/4 is 9. So I know that 6 is my common ratio, and thus I find my equation. And this is a pretty hard example, I'll be honest with you guys, but you guys are up for a challenge. Now this next one's a bit easier. So starting value is 1, 2, 3. So I know that point 0, 3. So that tells me it's going to be y equals 3 times some common ratio to the power of x. So let's find another nice point, 1, 6. And then how about right there, 2, 12. So we can ask what's the common ratio? And it looks like to get from 3 to 6, I multiplied by 2. To get from 6 to 12, I multiplied by 2. So that's probably 2 to the x. And we can check the same way that we did the last one. So y equals 3 times something to the power of x. And let's use this point, 1, 6. So 6 goes in for y, 1 goes in for x. What can fit in the parentheses such that when we raise it to the first power, multiply by 3, we get 6. The only thing that works is 2. So I know that this rule is spot on. And that's it for this video. If you watch this video, you can put fish on your test for 1 extra credit point.